We will now take a look at the convolutional neural networks. It has a different architecture and different idea behind it. So in convolutional neural networks, each layer basically consists of filter banks where fixed bias terms are added to each output and the result is passed through a nonlinearity. The filters are called the receptive fields in analogy to the processing, for example, in the retina of the eye. The filter coefficients and bias terms are then optimized according to a target function and a loss function, which computes the distance to the target function. Let's take a look at Python Keras convolutional neural network example. So most of neural network development is done in Python. It has very powerful libraries for it. For example, Keras, Theano, that used to be very popular, but nowadays it's not so popular anymore. I'm not sure if they are still developing it or if it's already deprecated. But we have TensorFlow and PyTorch. So here you can read more about Keras. In our example, we want to detect a signal in a sequence. In this case, we want to detect a ramp that is produced by this Python function here. We want to use a convolutional neural network to detect this ramp. So in a Keras example, first we will define our input data and our desired output. It's called the target. For the input, we will prepend and append a few zeros to the ramp function, such that the goal is that the neural network has to find the position of the ramp. So here we have our ramp. We have 9 zeros before, 9 zeros after, and our ramp has 5 numbers, so we have a total of 23 numbers. So Keras expects a certain shape, and we need to expand some dimensions so to prepare that our input has these expected dimensions. In the dimensions of the Keras that Keras expects is an input with the shape that is given by the batch, the length, and the number of channels. So batch here is the number of training examples. In our case, we have just 1, so our batch is equals to 1. The length is the length of our signal, so here we have our signal has 23 numbers, and channels are the channels of our data. For example, it can be stereo, so we would have 2 channels. It could be RGB, we would have 3 channels, but here we only have 1 channel. So the target signal will have the same size in this case, because we use a causal network that returns the same number of samples at the output as the input, and we will set up our target containing all zeros except for a 1 at the time of the detecting the pattern. So we will detect the signal at its end. We will detect the ramp at its end. So we have here zeros, and then we are having 1 at this position. So we will input this. So we have zeros, then we have a ramp, and then we have zeros, and the target is just a 1 when the signal ends. We also need to change the dimensions, and then we will start setting up our network model. So we will use sequential, then we will add a convolutional layer. This is how we do it. We define a model using sequential, and we add this convolution 1D. So we will have 1 filter. The size of this filter is equal to 8. Stride is equals 1. We will use causal, as we see before. We will choose linear activation, and we will not use a bias. We will initialize our weights using the Glorot uniform initializer, and we need to pass the input shape. So the input shape is a vector 23 and 1. So a filter here is used to detect a pattern. It will be similar to a matched filter that we've seen in our lecture Advanced Digital Signal Processing, in lecture 13, that you can find in our website. So the kernel size here is the size of our filter's impulse response. So here it can detect patterns of length of 8 samples. Strides here means that there is no downsampling of the signal. A padding causal means that there is zero padding of kernel size -1 zeros before the beginning of our signal. So the activation is linear means that there is no nonlinearity after the sum. So we are not using a sigmoid or hyperbolic tangent. We are not using a nonlinearity. Bias equals to false means that the bias is 0. And for the random initialization of our weights, we are using this Global uniform. And the input phase is the size of the signal at the layer's input. So then we need to compile the model and specify the used error function and the optimizer. So we defined our model here, and then we need to compile and we need to specify the error function. So it's called the loss function, and here we are going to use the mean absolute error, and we will use the optimizer called ADAM. So loss here is the error function, in our case the mean absolute error between the network output and the target. The optimizer is the optimization function to use to obtain the best weights. And here we are going to use ADAM. So after we compile the model, we specify the loss function, we specify the optimizer, then we can train the model using fit, and then we give the input, the target, and then we give the number of epochs and the batch size. So epochs is the number of iterations the optimizer will use, and batch size is the number of examples that we will have. In our case here is just one, but the batch size determines how the update of the weights will take place, and the epochs is the number that it goes through. So if we have, for example, we could have two batches. So we have 2 examples in our data set, and then we could set, for example, the batch size equals to 1 or the batch size equals to 2, and the epochs is how many times we will go through all the data set. So if we set the epoch equals to 1, we'll just have 1 iteration. So if we set it to 2, then it will go to the first input, the second input, and then it will do it again. So it's the number of iterations that goes through all the data inside the data set. So after the optimization finished, we can use our model for prediction. Here we want to detect the signal. So usually a separate test signal is used that is different from the training signal, but we're just giving here a very simple example, not going into the detail. So there are much more than what is written here about batch size, about the epoch. So we will just use the same input for testing. So here we are making a prediction. We can also read the resulting weights using this. So the first index of refers to the layer. Here we only have one layer, so we have the index 0. Then the next index refers to the input dimension, the next to the output dimension. So here we have only one output neuron, so the index is 0, and finally the channel index also is 0. So we have our filter weights. We get the weights here, and we get here W of 0, and then we have this way we get our filter weights, and we can also save these weights for future use. So there are many ways on how to save. We can save the full model. We can save that includes all the definitions. We can save just the weights. So depending on your application, you can save different weight. Here we'll just save the weights using Pico. Now we can plot the output of the neural network, the weights and the input using this part here. So when we put everything together, you can see the Professor Schuller example code and Gerald's simple ConvNet is a simple program that uses a convolutional neural network to obtain a matched filter. So, and we will detect the signal. So we start by importing all the libraries. We are going to use Keras and import the sequential model. We will import layers like the dense layer. We have activation. We have a convolution layer. So in this case, we are not going to use all of them. We're just important for future use. Then we have this function that will generate some artificial data in a NumPy array. So this is where we have our ramp. We will use we will make it a unit L2 norm, so we're normalizing here this command. Then we will reshape, so it's in the shape that Keras expect. So from here we have our input signal x, which is a ramp function already shaped for how Keras expect. Here we will have our target function, which is a 1, detecting the signal at its end. And then we also reshape for Keras, and then it will return. Next, we have a function to generate the model. So we discussed this before. So we have here our convolutional layer with all these parameters. We define our loss function, the optimizer we're going to use. We compile and we get a compiled model. So for example, here is just so we can see we have generate data. So we have our input and our target. So the final shape is 123.1 for the input and 123.1 for the target. So they have the same shape. Then we have our model using this generate model. Then we train using 5,000 epochs. We evaluate, and then we will make predictions. Then we get our weights. So here the model is training and it's computing the loss, and we see that the loss is going down, and down until it to go through all these epochs we define, and we see that the loss is much smaller than when it started. So here we have our predictions. We can save our weights, and here we have a plot. So after the 5,000 iterations of the optimization, we have here, this was our input signal. This is the weights, and this is the neural network output. So remember, we had a 1 at the position 16, so at the end of our input ramp, and we have here our network output. Oh, you can also compare these weights and the plot to the match filter, which we saw to detect, which is used to detect a signal with a maximum possible signal to noise ratio on lecture 13 on advanced signal processing. And we see that in the matched filter case, the weight should be the signal to detect, but time reversed. So here is a reverse ramp function. So this should be, we can see like this is our weights for the matched filter. And we had the input signal here was the ramp, a bit different than what we used here. And the thing is because we specified a target function which has only a very narrow peak, and this is what we observe at the output of the convolutional neural network. So this may not have a maximum signal noise ratio, but a more narrow peak at detection, which enables a more precise location of our pattern. It's interesting to see that even though it's called a convolutional neural network, a lot of libraries, they don't calculate the convolution, they calculate the correlation, the cross correlation, which can be seen as a convolution but without the reversed impulse response, so without the reversed weights. So in future examples, when we are seeing convolutional neural networks as filter banks, we need to take into consideration what's the impulse response, how to read out the impulse response from the weights. But this is another topic.